C. Angular position of fringe. Similar to the case of double-slit interference, the path difference at angular displacement theta on the screen is given by d sine theta. A bright fringe is found when the path difference is n lambda. The distance y from the central bright fringe, which is called the zeroth order fringe, is given by d tangent theta. These two equations may let you find the separation between different fringes. For example, for a 300 lines per millimeter grating, green light of wavelength 550 nanometer with a screen grating distance of 1.2 meter, the first, second, and third order fringe are found at y equals 0.201 meter, 0.419 meter, and 0.684 meters respectively. You may notice that the fringe separation is not constant for transmission grating, but increases with the order of fringes. Hence, you must use the above two equations to calculate the fringe separation, case by case. So why the fringe separation for double slit is almost constant? Just because the double slit interference has a much smaller angular width, so that the angles theta are much smaller, which makes sine theta close to tangent theta, and hence resulting in almost equal fringe separation, independent of the order of fringes. The largest possible order of fringe, n, is given by the case when theta equals 90 degrees. Hence, d over lambda. Form a T with two meter rules and pointer towards a LED. Hold a plane transmission grating at the end of a meter rule pointed at the LED. Fill the LED through the grating. You will see an interference pattern. Ask your partner. Prepare a pen and move along the ruler so that it is pointed at one of the maxima. Measure the distance L of the first order maximum from the central maximum. Using the equation, you may find the angular position. Repeat the above steps with other maxima. Plot a graph of sine theta where theta is the angular positions of different orders of maxima. Find the slope of the graph. Find the grating spacing d according to the label on the grating. You may now use the equation to find the wavelength of the light source. Example 3. Highest order of fringe. The wavelength, the screen grating separation, and distance between second-order fringe are given. Using the above equation, you may find the grating spacing. Example 4. Multicolored interference pattern. It is a simpler question than example 3. You should better read this and then read example 3. Using bright light, the interference patterns of different colors overlap. The central maximum is still white, with all the zeroth order maxima overlap there. The other maxima are found at slightly different positions so that colored spectra are observed, and the spectra is wider for higher order maxima. For any particular spectrum, the inner edge is always violet, while the outer edge is red, as violet has the shortest wavelength. Also note that the third order maximum of violet is given by the formula sin theta equals 3 times 400 nanometer d over a, which is smaller than that of the second order red, sin theta equals 2 times 700 nanometer d over a, and so the second-order spectrum overlap with the third-order spectrum. Example 1. Observing interference pattern of white light. The color spectra of white light is produced by grating. Different colors are identified at different positions. D. Interference patterns produced by double slit and plane transmission grating. You should have noticed that a plane transmission grating produces brighter, sharper, and more widely spread interference pattern. It can be explained readily by comparing the following equations, which look pretty alike. A sine theta equals n lambda for double slit and d sine theta for n lambda for grating. The grating spacing is usually much smaller than that of slit separation of a double slit, which then produces a larger fringe separation. The more slits in a grating also allows more light to pass through and hence produce a brighter interference pattern. E. Estimating the wavelength of monochromatic light using a grating. By measuring the separation between bright fringes, you may find the wavelength of light using the two equations mentioned above. Example 5. Estimating wavelength using a grating. This example demonstrates how you may measure the wavelength of a monochromatic light source, which is a LED in this case, by producing interference using a grating. What is interesting is it makes use of a graphical method, which measures the angular position theta of different orders of maxima, and plot a graph of sine theta against order of fringes n. As d sine theta equals n lambda, the slope of the plot should equal to lambda over d, where d is the grating spacing. Do check point 5 below.